The first one will be Professor Santiago Badia. He is professor for continuum mechanics at the University of Politècnica de Catalunya, and also is the leader of the large-scale scientific computing department of the International Center for Numerical Methods in Engineering. We know each other for quite some years now, although he's very young. I already know him for a couple of years. Professor Badia has done excellent work over the years, published a huge number of papers that are really worthwhile reading. He has received a big number of awards, so this gave me a hard time to study, to remember most of them at least, I would say. So, and I think I should start with one award that is very important for this community here. So he was one of the recipients of the ECOMAS Best PhD Thesis Awards in 2006, and also got the Best PhD Thesis Award from Cimne, from the Spanish Association. He also received the Juan Carlos Simo Award for the Young Investigator Award for the Best Young Investigator in Computational Mechanics. He also received an award from the Spanish Association for Computational Mathematics in 2012. He received different fellowships, including the Marie Curie Fellowship and some others. And I think something which is also very useful and helpful for what he developed over the last years, he also holds an ERC starting grant and also a proof of concept grant from the European Research Council. And this gives him the ability to be independent in a nice surrounding, I would say. With this, I would leave it, and I would like to call Professor Badia, which, by the way, is in a sense half German, as we just joked, because he was born in Mallorca, and as you know, Mallorca is occupied by many Germans. I can say this, I'm not German, so I can say it. So we are happy to have you here and looking forward to your presentation, please.
Okay. So today we'll talk about an scalable multiphysics and multi-scale framework that we have been developing during the last years. So first, let me motivate a little bit this talk. We are now in transition from current supercomputers, which are of the order of 10 petaflops per second, to the future exascale systems, which are going to reach the exaflop per second. So we expect to have in, let's say, 5, 6, 7 years, 100 increase in terms of performance for supercomputers. But the thing is that this increase in performance is going to be based mainly on increased levels of concurrency. So somehow we will have to deal with, let's say, multi-million core in a broad sense, supercomputers. So this is quite a challenge, how to efficiently exploit millions of cores in computational science and engineering, but for sure, that's also a great opportunity to simulate problems that are now out of reach. Today I will talk just on one of the particular challenges that we have, which is how to develop weakly scalable algorithms. Very briefly, a weakly scalable algorithm is the one in which if I give you X times more processors, you will be able to solve an X times larger problem with the same amount of time. So that's very nice because it allows us, as we have more and more processors, we can go to higher accuracy or just to solve larger problems. So in computational science and engineering, these kind of methods are going to be very interesting. But weak scalability is not so easy to attain. It's not only a computer science issue. It in fact requires quite advanced mathematical algorithms and also very advanced implementations of these algorithms. Now, it's a synergy of two worlds. Because, for instance, if we focus on one of the bottlenecks that we have in implicit simulation, which is, let's say, the linear solver, if we use quite a naive approach for the linear solver, let's say no precondition at all, and we do a weak scalability analysis in which what we do is to increase the problem size and to increase the number of processors in such a way that at every processor we have the same local problem size. So if we do that, and we see, for instance, here the number of iterations that we get, if you do not precondition, we know that the number of iterations blows up. If we use quite rudimentary one-level domain decomposition methods, the number of iterations, everybody knows, increases, not so dramatically, but again, in an acceptable way when we want to go to very large scale. Here we are just with some hundreds of processors. So if we want to solve real large-scale problems, the main approach and the better approach nowadays is to use parallel algebraic multigrid. And there are these excellent libraries developed by US national labs, like Trilinos in Sandia or Hypre in Lawrence Livermore. Even for these extremely efficient implementations, it's a very non-obvious task how to scale up to the largest supercomputers today. So mainly because there are some problems related to the increase of the communication and computation ratios as we go to larger and larger problems. So out of the picture, it seems that there are lots of work in our community to really deal with exascale to computational science and engineering. And this is only a part of the problem for implicit solvers. This is only part of the simulation pipeline. Another approach that we would consider is to use domain decomposition for large-scale simulations. I would say that domain decomposition is more a framework than just a linear solver, but on the other hand, it's not a general purpose solver. It's more, let's say, motivated from grid-based methods, but for most of us, that's not a real bad point. It's more or less a divide and conquer approach in which we have a finite element mesh. We produce aggregates of finite elements, subdomains. Here we have the subdomains, and we compute local problems in every one of the subdomains. So with this approach, we can easily exhibit concurrency in our implementations. Two-level domain decomposition methods can be found, which are, in theory, on paper, they are weakly scalable. We have, for instance, the groundbreaking work by Mandel, the balancing Neumann-Neumann method, FETIDP by Farad and co-workers, or BDDC method that was developed by Dorman and other researchers, more or less at the same time. So they are scalable on paper, but it's harder to make these methods scalable up to, let's say, some tens of thousands of processors. In order to improve a little bit the situation, we can use multi-level domain decomposition. In particular, this preconditioner here is one that allows a straightforward extension to multiple levels. So this is more recent, but this kind of methods, as I will show today, have lots of potential. What we need in order to implement multi-level domain decomposition, the first thing what we need is to create automatically in our computations a hierarchy of meshes, and also on top of the meshes, coarser meshes that we are going to create, to put some kind of functional space. For instance, here we have a finite element mesh in which we want to compute our problem. We can create aggregates of these finite elements, create the subdomains at the first level. If we have a two-level method, this is all, but if we want multi-level domain decomposition, we can proceed in a recursive way, consider these subdomains as elements again, aggregate them, and produce the subdomains at the next level. This would be what we require in a multi-level domain decomposition implementation. And in the multi-level domain decomposition implementation, what we need to do is to solve, again, local subdomain problems, but now local subdomain problems at all levels, here, at all the subdomains here, and at all the subdomains here. So the other thing that, let me put a comment on that, this kind of multi-level domain decomposition methods have a very similar flavor to multi-scale finite element methods. There are so many finite element techniques out there, but I would say that there are not so many scalable and practical implementations of these methods. With the approach that I'm going to show today, we will be able to implement in a very efficient way multi-level domain decomposition method, but it also opens the door to use this framework as multi-scale solver. So this is the main motivation, an extremely scalable multi-level and multi-scale framework. This is the first part. Second, I want to apply the framework that I'm going to develop to the implementation of multi-level balancing domain decomposition, and analyze which is the practical scalability of these methods on current supercomputers. And finally, if I have some time, I will try to put a word on how we go to multiple physics using block preconditioning. So let me say that all the things that I'm going to show today have already been implemented in our in-house code, FEMPAR, that we are about to distribute as an open source software soon. So let me start with the framework. Since we have a non-overlapping domain decomposition method, we have an element-based partition of the finite element mesh. We start with the finite element mesh. We consider a partition of the mesh into pieces, and let's say every processor has its own piece of the mesh. Certainly, we need to know how we glue together the different meshes, so we need some kind of information of the ghost elements, but very limited one. With this information, we can create the communication objects. And the communication objects are the following. For instance, here we have the interface nodes and edges. And what we do is to classify the interface nodes and edges among processors, among subdomains, based on the subdomains they belong to. For instance, these vertices and edges belong to the red and the green subdomains, so they create an object. Those here belong to the red and the blue one, so they become an object. Those will be between these two. And finally, this one that is the only one that belongs to the three different subdomains for this silly illustration. So at the end of the day, at every processor, this is something that we can do in parallel, and at every processor, the information that we have is the piece of the mesh, and also the communication objects for needless network communication. This is all we need. And now, a very important thing for our framework is to classify these objects from a geometrical point of view. There is an automatic definition of this classification. We are going to classify the objects in terms of faces, edges, and corners. Here we have a 2D illustration, so we're going to classify these 4 objects into edges and corners. So if we apply this definition, which is general, can be applied to whatever finite element mesh we have, we would end up with what we expect. No? These 3 here are edges, and this guy here is a corner. So once we have done that, what we can observe is that we have created a coarse triangulation. We have started with a fine triangulation, distributed, and now we have a coarse triangulation in which the finite elements now, not finite elements, the elements now are defined by aggregation of finite elements here. So this element is going to be the aggregation of the elements in this processor. The same for the others. And finally, the edges and the vertices are also defined by aggregation. For instance, the edge in this coarse mesh is defined by aggregation of corners and edges in the fine mesh. So this way, we have ended up in an automatic way with a coarser mesh. Now, on top of this coarser triangulation, what we want to put is some kind of finite element type space. The idea is, as typical in finite elements, we are going to put degrees of freedom on top of these coarse objects. And typical definitions of these coarse degrees of freedom, one typical definition would be the following one. We want to put a degree of freedom on this coarse edge. So we can define the coarse edge for a given function as the mean value of the function on the edge. So this would be one particular choice of a coarse degree of freedom on an edge. So now, when we have that, we can talk about the following finite element spaces. This space is the original finite element space in which we want to solve our problem. We could also think about an assembled space in which is the tensor product of the local finite element spaces, no assembly at all. And then we can also consider an intermediate step, an intermediate space, which is this B-bar space, in which we only enforce continuity on a reduced number of quantities, let's say the coarse degrees of freedom. For instance, here, we only enforce continuity of the coarse degrees of freedom among processors. So it's clear that it's somewhere in the middle between these two, because this one requires full continuity, this one does not require any kind of continuity, and this one only requires reduced continuity. So now we can think in 2 different ways. We can consider B-bar as a multi-scale solver, because as you can see, we have like a component which is, has a high resolution in the fine mesh, but then the communication, the continuity is defined on a coarser mesh. So somehow it's some type of multi-scale solver. In many applications, we could be interested just in solving the problem here, and it would be enough. But in many situations, what we want to solve is the original finite element problem, and in this case, we can compute the solution here using, for instance, some iterative Krylov method and precondition the problem with corrections that require to solve in this space. Okay? So we have like two choices: to use the solution as the solution of our problem, or to consider that as a preconditioner using iterations. So with a particular choice of the coarse degrees of freedom, what we recover is the balancing domain decomposition by constraints domain decomposition method. Another very important thing of this multi-scale B-bar space is how we implement the solution of a problem on this multi-scale space in an efficient way on supercomputers. So what we can do is to decompose the problem into two components. The space of bubbles, which is the space of functions here that vanish on the coarse degrees of freedom. Since they vanish on the coarse degrees of freedom, and these are the only doves that involve coupling among subdomain, this computation is local. And then the other part, the other component, is the coarse space, which is going to provide us the values on the coarse degrees of freedom. And this coarse space is going to be called V1. So now we can define for this coarse space, we are going to define it in such a way, that's a very important property of these methods, that the shape functions associated to the coarse degrees of freedom are orthogonal with respect to our, let's say, the form of our problem to the bubble component. This is orthogonality is possible. For instance, we can define a basis for the coarse space, a set of bases, one shape function, one coarse shape function for every coarse degree of freedom. For instance, we can think about this corner here in the partition, and we can here what I show is the coarse shape function related to this coarse degree of freedom. It only involves to solve, in order to enforce this orthogonality with respect to bubbles, it only implies to solve local problems on the surrounding subdomains, so it's something that we can do efficiently in parallel. This would be the shape function related to an edge degree of freedom. Here we impose that for this function, we impose the mean value equal to 1 and 0 on the rest of coarse degrees of freedom. We compute, we extend it solving local problems, and this is what we get. We can observe that the solutions are discontinuous because the only thing that we're enforcing is the continuity of the mean value. So now that we have this decomposition and this orthogonality, the very important thing is that the problem in the multi-scale space B-bar can be decomposed into two parts, which can be computed independently: the bubble component and the coarse component. So the bubble component is something that we can efficiently compute in parallel because it's embarrassingly parallel, it's local, it only involves local problems, and the coarse problem is the most complicated thing because it's basic for scalability, but it's a global problem that increases with the number of processors. So this is the main complication when we go to practical implementations. So the first thing that I have to say is that to exploit in our implementations this concurrency between levels, between scales, is basic for getting the scalability results that I will show you in a moment. So let me put this illustration. We want to solve the problem for this seed example here. If we have as many processors as subdomains, every processor has its own piece of the mesh, we will require to solve local problems in every one of the processor, and then probably one of them has to solve the coarse problem. Okay? But this is the thing that destroys scalability, because in general, for practical implementations, we have lots of processors in the fine component, and then for efficiently solving this problem, we cannot use all of them, just a very small part of them. So we have a tremendous amount of idling here that destroys parallel efficiency and scalability. So exploiting in our implementations concurrency, what we can do is to put processors, not only as many as subdomains we have in the final level, but also processors for the next levels. So here, for instance, every processor only has one level duties, and the most important thing is that we can overlap communications and computations among levels, so reducing dramatically idling and improving a lot scalability. So in FEMPAR, what we have is what we call an interlevel overlap bulk asynchronous implementation, because different processors are doing different things at the same time. Now, very important thing is that I started with V0 space, which was the finite element problem, and I have created this B bubble and B1 space, the coarse problem. Now we could go again and start with the coarse space, and everything can be applied verbatim. So this way, we can easily create, if we have a recursive implementation of all these things, a multi-level method in a quite a straightforward way. So in a multi-level method, what we want to have and what we have implemented is, for instance, here we have the level 1 subdomains that are aggregated. Here we have the level 2 subdomains, and let's assume that for the third level we only have one processor, so all these are aggregated into one, let's say, subdomain at the third level. So this would be a third-level method, and what we are going to have in our implementation are processors dedicated for every one of the levels. And what we want to create is a workflow in which we can overlap all levels computations. So using finally, the key aspects of what I've presented for having the scalability results that I'm going to show are, first, that our implementation is recursive. We have implemented everything in a recursive way. So now the number of levels that we want to use in our multi-level domain decomposition method is arbitrary. It's an input. So we can put as many levels as we want. The other very important thing is the inter-level overlap implementation that I commented before. These are the two key aspects of the implementation, of our implementation within FEMPAR. So now if we want to solve a linear system with all this machinery, here we have, what we're going to use is a, let's say, precondition conjugate gradient, or GEMRES, with multi-level BDDC preconditioning. As I said before, BDDC is a preconditioner that uses these multi-scale spaces that I have defined before. So here I have the result for, say, the picture for 3 levels. And I'm not going to get into details, but the thing is that we have to analyze all the tasks that we have in the algorithm and seek a way to classify them among levels. So we can do that. It's quite a little bit tedious. And finally, what we can observe is that we have lots of potential for overlapping. So here, what we observe is that we have 3 overlapping areas, but the most important thing is the following. In a weak scalability scenario, what we are doing is to increase the global problem and the number of processors. In this way, the local problem size at the level 1 processors is constant. The local problem size in a weak scaling analysis is constant. And since here we have fixed only one processor and we have fixed the number of levels that we are going to use, the problem here is going to increase with the number of processors. So this is the guy that at some point is going to kill me. And what I expect 3 different situations. The first one, in which the critical time is the one of the fine component. In this case, the others have to wait when we require inter-level communications for this one. So this is the critical path. In this case, what we expect is to have perfect scalability, because all the things that we have here do not depend on the number of processors, so it has to be perfectly scalable. The second situation is the one in which we have a very loaded second level problem. So in this case, what we expect to have is something like that. We can have also perfect scalability because the local problem size at the second level at these subdomains is also constant, but it's certainly not optimal because here we have many processors that are waiting till these guys will finish. So the idea somehow is that it's better just to have this as a critical point, because usually here we have like 1,000 times more processors than here, where we have like 1,000 times more processors than here. So the idea is that we want this to be the critical path. And if at some point this is the critical path, the situation is the worst one, because the problems that we have to solve here depend on the number of processors. So what we will observe is degradation, is a loss of scalability. So our goal is to make this the critical path. So we have to play with the coarsening ratios that we are going to use, the number of levels. We have some heuristic formulas for that. And here are the results that I want to show you. This is a 3-level method. We have used just 2 levels. For the, this is the typical benchmark, a Laplacian problem for weak scalability analysis. And for this problem, in 3 dimensions, what we're imposing is continuity of corners and edges, mean value on edges only. In this case, here we have the number of iterations that we require, and here we have the total time, the real time that it requires to solve the problem. And what we can observe is that with our implementation, we can get extremely nice weak scalability plots till the whole Yuquin supercomputer in Germany. This is the computer in Europe with the largest core counter. So we have played with different local problem sizes. We increase the number of processors, we increase the size of the problem, and we keep constant the local problem size. So the idea is that when the local problem size is very small, it's really hard to make the first level tasks dominant. But even in this case, you can observe these very nice results for only 8,000 processors in 8,000 elements in one subdomain, which is quite difficult. We wouldn't be able to do that without overlapping and without multi-level. We do the same for elasticity. We have an elasticity benchmark for weak scaling. And in this case, we observe more or less the same, the number of iterations. We know from Theo that the method is scalable, weakly scalable. And we go to the practical implementations. We observe here the number, the results that in time till almost 500,000 processors for 3 different local problem sizes. So for 15 to the cube, you start losing a little bit of scalability here. So what we would need in order to have perfect scalability would be to introduce a 4th level to solve the 3rd level problem. But this is just that's in our implementation. And I'm going to go a little bit further. So I'm going to take the Yuquin supercomputer, the whole supercomputer, and I'm going to do oversubscription. I'm going to put 4 subdomains at every processor and end up with almost 2 million subdomains in domain decomposition. For getting these results, I will require to use 4 levels in the BDDC method, and these are the results that we obtain. This is practical time. This is CPU time. These are the plots that we obtain. And you can observe that you have perfect scalability till 2 million subdomains with even only 1,000 elements per processor, which in my opinion is quite impressive result. So now we go also to multiphysics. I don't have much time to do that, but in our code, what we usually do is to use sure complement-based approximations. So what we require is to solve finally 1 physics problems after we do these sure complement approximations. And for these 1 physics problems, what we use is our multi-level domain decomposition framework. So we have used, okay, I'm going to talk about that, but we have a software abstraction based on runtime polymorphic data types that allows us to easily implement weird block preconditions in just some lines of code. So we have applied that, for instance, for turbulent incompressible Navier-Stokes problems, in which we use segregated Runge-Kutta methods, that we call it, this type of methods. They would think of these methods that they are high order, but when you integrate in time, they decouple velocities and pressures, that you can keep high order of accuracy. They involve to solve this matrix, but a perfect preconditioner for this matrix is a BDDC approximation of a Laplacian, and then we can have extreme scalability for the simulation of turbulent flows. We have also applied that for thermal MHD, which is a 5 times size multiphysics problem. And for that, what we use is something that I didn't describe here, which is a block recursive implementation of block preconditioners. And just as a conclusions, let me say that I presented a scalable, multi-level, and multi-scale framework. The key is to exploit the concurrency among levels and put more than 2 levels if it's possible. So these are the two things. Recursive, our implementation is recursive. We can put an arbitrary number of levels. This is an input of their code. And interlevel overlap, so it's bulk asynchronous. It's very important to get these results. We have remarkable scalability. Now our code is in the HiQ lab of the most scalable European codes. And as far as I know, these are the largest scale problems in domain decomposition. And we have, when we go to multiphysics, we combine all these with block preconditioning. So that's all, and thank you very much.